I need to record this for posterity. I don't want to see me on videotape.
The world famous.
We're all famous, yeah. So, well, I'm Lynd Bacon. I'm sort of primarily an applied quantitative methods person. I do most of my work in the area of marketing science. Most of my training is in areas like econometrics, psychometrics, and machine learning. So I'm not like a legitimate statistician, although I've had a certain amount of coursework and some decades of experience in applications, and I do a little teaching periodically on the side. Currently, I'm teaching a graduate program for Northwestern on a distance basis. So that allows me to avoid going to Chicago in the winter, which I think actually they just had frost this morning up there. So I kind of gloated this morning for my faculty. But what I'm going to talk about today is doing Bayesian statistics in R. And this may be new to you in at least two respects, depending on your background. You may be unfamiliar with Bayesian statistics, you may be unfamiliar with R, or you may be unfamiliar with both. Or you may be unfamiliar with some of the application that I'll talk about, which is all fine. But I'm not knowing anything about it, I tried to pick sort of the right middle of the road, so that to me is a compromise that's not going to satisfy anyone. So, but it's Friday afternoon, and I appreciate you being here. I also realized after I pulled some slides together for this that I probably didn't have enough jokes given that it's Friday afternoon, so if you'll bear with me, I'll periodically put in one or two. So I probably should have basically introduced myself as a reformed frequent statistician. Although my Bayesian roots go back about 3 decades at the University of Chicago, which is where I first got baptized into the Bayesian world. And it's gotten a lot less crazy and maybe more popular since then. My knowledge is definitely skewed in particular areas. So, like I said, I'm not like a legitimate statistician. I'm not a math stat person. I've basically learned things that I've had to learn either because I'm teaching them or because I needed to use them. So I've been fairly eclectic in my approach to things. So what I'm going to talk about is Bayesian statistics in R. I'm going to talk a bit about why would you use R for this. And I'll also give you some reasons why you might do it at all, why you might be interested in this way of thinking about statistics. I'm going to talk about a class of methodology that, by and large, much multiplied and theoretical work is done with these days, and that's with simulation methods, Markov chain Monte-Carlo simulation methods, which are really indispensable for solving the kinds of difficult estimation problems that we deal with. And I'm going to finalize by talking about an application in the area of measuring the structure of preferences using data from a technique that's called choice-based conjoint measurement. And I'll tell you a bit about that, so it's not so mysterious. But it's actually very, very broadly used. Okay. Then if you have questions, jump right in.
Are your slides online anywhere?
I will post them online, or maybe I'll pass them to one of you guys.
I'll put them on GitHub.
That way we can revise them as we go. I'm sure there's going to be some errors in here. There's always something when I look at my slides and go, crap, that equation's wrong. Hope nobody notices.
Hey, Ken,
So,
do you have a link on our Meetup website for the GitHub?
I'll put it up there again.
Yeah, right on the front page so
Okay.
that people
Okay,
will miss it.
I guess we can add it, like details probably, right?
I don't know. Yeah. But that would be good, right?
We'll definitely do it.
Who's never seen this demo? Has everybody ever seen this somewhere in your education, or you know what that is? Who's never heard of Thomas Bayes? Has everybody heard of Thomas Bayes? You know who he was? How long ago he lived? What he did for a living? You're shaking your head. You don't know
I
about
don't know the details. I have heard the name a lot, but I don't know.
I've always been suspicious because in the Northeast there's been branded English muffins called Thomas's and Bayes. I never figured that out. But that's not the same Thomas Bayes, I don't think. Thomas Bayes was a clergyman who lived in the 18th century. He was also a member of the Royal Society of London. So he's also considered to be a scientist. It wasn't unusual, back in the day, oftentimes for scientists to earn their keep, they had to have roles in the church. Some had to be astrologers. I think Kepler was the court astrologer, the astronomer Kepler. But he told people horoscopes. That's how he got paid. Well, people who worked in a church, you were basically educated either if you're in the clergy or you did something like some kind of science, mostly physicians. So Thomas Bayes basically wrote a lot about probability, but it wasn't until after his death that a colleague of his, Richard Price, actually presented the work that we know today. it's Bayes' theorem. And this is what it is. I'll tell you what this is in a minute. Price presented a talk to the Royal Society about a year after Bayes' death in 1762 or 63. And then in keeping with the custom of the day, he then basically submitted a paper that was his presentation. And that's the paper that you can find online. And it's sort of an interesting read. But Bayes never wrote this equation. But here's what it is. You know, in the simple case where we have events A and B, that there's some uncertainty about the occurrence of, what this equation says is that the probability of observing event A, given that B occurs, is equal to, in the numerator here, the probability that B occurs given that A occurs times the probability of A divided by the probability of B. This is what's known as Bayes' theorem. And it's actually very easily derived from just the basic rules of conditional probabilities. Bayes never wrote it down. But Price, I guess, was listening to him and he wrote it down. And we probably don't need to go through this because this is just a simple derivation. So at the very top of equation 1, we have just the basic rule of conditional probabilities, the probability of D. Probability, get in the door. Okay. Conditional on the occurrence of A is equal to the joint probability of B and A occurring divided by A. And it turns out if you just do a little simple algebra and take advantage of symmetry in these relationships, you can get two different versions of Bayes' theorem. It's very handy equation. Much of what we do today is sort of based on elaborations on it. Anyway, that's who Bayes was. No one, by the way, as far as I can tell, no one knows what he really looks like. There's all these pictures of a guy with like a, you know, some kind of cleric's collar or something, but nobody really knows. Now, the way that we often write it when we talk about fancy-dancy models is we write it this way. And we put in some Greek characters because it makes it look more scientific. Right? But basically, this is the same statement here, although instead what we've done is we basically identified a set of parameters whose posterior distributions we want to identify, represented by the thetas. The D is data that we've observed. So on the left-hand side, what we have is the joint posterior conditional probability distribution of parameters theta is equal to what's on the right-hand side of that equation. So just the common terminology is what's on the left-hand side is the posterior distribution of theta. And of course, for interesting problems these days, that's a very high-dimensional joint distribution, 3,000 dimensions. Therein lies the challenge in estimating these next values. L is basically the likelihood of the data given the values of theta. P theta is just the prior distribution of theta, and PD is just the density of the data. It's a constant, right? So because that's a constant in the denominator, it allows us to take advantage of a very convenient proportionality, and that's down here at the bottom. And most of the approaches that we use to estimate the posterior distributions of these thetas take advantage of this proportionality. We can ignore that denominator. Okay, so far. Getting more scientific. Get a few more Greek letters in there. But before we get to that, it's reasonable to ask why it is that people use Bayesian statistics at all. Certainly it hasn't always been very popular. It's been the cause of some rancor and a certain amount of suspicion on the part of the traditional statistics community. But there's a variety of reasons that Bayesians give. One is, although this is not always viewed as a tenet by all, and that's that you can incorporate prior knowledge in your estimations. That's what those priors are. They're your best guess at the distribution of those parameters before you observe data. So that's either good or bad. My experience, anecdotal experience with decision makers like managers, they kind of like that idea. They don't understand why. But it makes sense to them that somehow they should take advantage of what they've already learned. Then they get data, and then they update what they learned. Bayesian estimators are shrinkage estimators, and that means that actually they're less vulnerable to random variation and inflating and causing bias in the values that algorithms converge to when estimating them. When you use Bayesian statistics, you can avoid using asymptotics. So you don't have to make assumptions about what happens with a statistical estimator as your sample goes to infinity, an asymptotic estimator. You just basically deal with the results that you kind of have. You can avoid now what's the increasingly disrespected null hypothesis statistical testing procedure. There's a lot of literature recently I think the last time I was here 2 months ago, we talked a little bit about that, the current kerfuffle about that. What's that journal? Basic and Applied Social Science, Social Psychology, where the editorial board just decided no more of this stuff. Right now, their solution doesn't seem to be great, and so some people I know actually have written the editorial board saying, well, you know, don't throw the baby out with the bathwater here. But anyway, there's some problems with it, and if you read people, statisticians like Andy Gelman, he's got a great blog he talks about this. There are other people who talk about it too. One of the other advantages in using these techniques, and in particular taking advantage of certain model architectures, is that we can exploit with what we refer to as information pooling, where we take advantage of the similarity between units to overcome certain problems with sparse data. And the example I'll give towards the end of our time together, you'll see how that's done explicitly to that particular type of model. We can estimate models that are not amenable to closed form solutions. The whole origin of the current practice was in solving very, very difficult physics problems in the Manhattan Project. So back when much of the work that had been done was declassified, it was published by people like Metropolis and Teller. And a lot of the early contributions to Bayesian thinking as we know it today was in the field of physics, not in biostatistics, not in social science, and so on. Because if you think about the problems they were trying to solve in the Manhattan Project, they were incredibly gnarly, to use the right technical term. They were trying to solve integral calculus problems in thousands of dimensions. And how would you do this? You could never solve these problems analytically. So instead, what they came up with was a series of methodologies that allow them to approximate those densities in high dimensions by step-by-step sampling, taking conditional random draws from each marginal distribution and then putting it all together again. And that's basically how most of the algorithms we use for doing simulation-based Bayesian estimation work today. It's the same approach, except in those days they just had rooms full of physicists with adding machines. And that's how they did it. I mean, just an incredible task of organizing the activities of all these people, mostly guys with ties, right? Sitting in a room with like Monroe hand calculators, and somebody keeping track of how it is that they were passing information from one iteration of the algorithm to the next. So it probably took a few years to do that. It didn't necessarily end up in the best product, that's for sure. But so anyway, that's another reason why Bayesians will say we use some of these techniques. Another benefit is that these methods provide kind of a natural way of treating missing values. Because in a sense, all the parameters we estimate are missing values. So if you have a missing data point, you just sort of estimate it in the same way. Because that's what we're doing. We're making inferences about things we couldn't observe directly. We put distributions on things. We turn the crank of these estimators, and then we get a prediction of what that thing would have been. So that's very nice. And then finally, and this one also kind of raises the hair on the back of some people's neck, but using these simulation methods, we can get arbitrarily precise estimates. Because it's now not a matter of the sample size we've got, it's a matter of how long we run the algorithms. So the longer we run, the closer we get to really being accurately representing the posterior distribution of some parameter. Now, it's a matter of diminishing returns, not surprising. So the precision increases proportional with the square root of R, or the number of iterations we're running, just like standard deviation decreases. But the point is, we may have a finite set of observations of data that we've observed, but the parameters of the models that we use to summarize those data, we can estimate by just running very, very long numbers of iterations. They're called chains, sampler chains, and getting more and more precise in our approximation of the distributions of the posterior distributions of those parameters. So those are what Bayesian is. Now, not surprisingly, there's some negatives to all this. One is, well, geez, you have to write full probability models for everything. So the math gets a little bit more demanding because you've got to incorporate the priors, and then ideally there's certain sets of priors that are easier to use than others. I won't spend a lot of time on that today, but there's some that work that others don't work, and you have to be sort of picky about that. And those are the dreadful priors that people refer to. This article published in the last 5 years, where that was actually part of the title, the dreadful priors, because you have to come up with priors. But it turns out in practice, in particular areas, there's enough accumulated knowledge, at least you get a sense of what everybody else is using, and either you're all wrong or maybe you're all on the same page. But it's a little bit easier than just sort of making up things around. So there's priors on the prior.
There's always the non-informative prior.
There's always a non-informative prior. That's right, or it's basically kind of like a flat prior. Now, ideally, priors are proper priors, right? So, you know, what that means is that it has a finite interval. Obviously, if you go back to the equation, you multiply something that has an infinite area underneath it, it's not going to help you with posterior. But, yeah, in fact, on informative or weakly informative priors are often used to basically read priors for things like variances, for example, depending on, you know, how your algorithms work. Computational intensity is a big drawback, or it is currently, although there's been a lot of advances in recent years on approximations and on making these algorithms run in a more parallel way. There are certain challenges in making them parallel because of the way they share information from one iteration to the next, and the way that parameters depend on other parameters. Because parameters have parameters in these models, they have hyperparameters. Results overload is another one. This actually, a lot of the work that I do is kind of a challenge for the recipients of some of the work, because in fact you get, you know, if you have a model that's producing, say, posterior distribution information on 4,000 parameters, and they'll have something to do with something like people's product preferences. You have to summarize that somehow for decision makers. And so you're always walking this line between making it as simple as possible for them, but somehow not allowing them to completely disregard uncertainty of things. So as it, you know, as Ed Deming once said, to paraphrase actually, the fundamental task of managers is to understand variability, right? So you want to kind of guide decision maker to use the information as best as possible, but you can't just like overload it. In fact, for the analyst, there can be a lot of overload too. So it's a good idea to have some pretty good analytic plan before you go into it and use all the information that's available when you run these simulations. Excuse me. And finally, explaining Bayesian inference to non-Bayesian. And this is a whole other kind of can of worms. But in fact, it's probably easier to explain it to non-statisticians than it is to explain it to non-Bayesian statisticians, because there's a certain amount of fervor around the issue. And if you're an academic, it can be a challenge also basically using Bayesian techniques in submitting to a journal where they can't find a reviewer, for example, to basically properly appreciate your methodology can be a real problem. In the world of decision support, though, it's a little bit different, because oftentimes we hide a bunch of this stuff from clients unless they're particularly adept at these things. Another one on here, that it used to be the case that if you were Bayesian, you were considered to be like a cult member. And Bayesians didn't really help themselves that much in that regard, because they used to write their own special songs. They had rock bands at their conferences. They had Bayesian rock music, you know. I mean, it was pretty crazy. So, you know, the group at that time, some decades ago, probably at least partly deserved the reputation. And they were also not necessarily as diplomatic in their criticism of non-Bayesian statisticians. But like I said, I tend to look at these things from a very collective perspective. I basically use tools that work, and oftentimes these tools work for me, although sometimes not without a little bit of pain. Okay, so what about Bayesian R? Well, there's a lot of reasons that you do Bayesian statistics in R. Many of them are kind of more general reasons why you do any kind of statistics in R. R is a very powerful programming environment. It has a very, very large array of packages. If you haven't looked at that, here, just take a look. See if I can find it. Is it going to show? Yeah. Oh, okay. So in the R mirrors, there are these things called task views. I can't actually show you the whole one. And task views are kind of moderated or maintained by a maintainer, and they keep track of all the different packages that have algorithms and tools for particular types of statistical applications. This is the one for Bayesian methodology, and it's very large. There's a whole variety of different techniques in here. These are all packages that people have written. They're more or less tested and usually correct, maybe not always. And here they are. I won't go through all these because we don't have that much time, obviously. But I can tell you that there's some general classes that are worth paying attention to. So there's packages that do Bayesian parametric statistics, which is most of what I'm talking about today. But there's also semi-parametric Bayes methods, and there's non-parametric Bayes methods, and they vary a little bit in their flavor depending on the area of application and who has been developing them. There's applications that are specifically developed for use in the social sciences, from biostatistics, which you're probably aware of, and in econometrics and in machine learning. Machine learning applications include things like Bayesian tree models. They're kind of sort of a Bayesian version of CART models, Bayesian model averaging, tools like that, that machine learning people have become particularly favorable. You probably know this, but the standard or baseline technique for doing document classification is a naive Bayes classifier, right? It's not really true Bayes, as a Bayesian we talked about it. And another very popular technique in machine learning these days is Bayesian belief networks. And it's also, again, sort of not true Bayes in the sense we're not working out these full probability models, but they're definitely Bayesian applications. So it's kind of all over the place. I've heard it rumored that, in fact, that very irritating helper paperclip they used to pervade Microsoft Office was also a Bayesian application. And it was learning to be irritating, apparently. Because there's a lot of stuff online about how you get rid of this thing, you know. But anyway, and there's also packages for learning or teaching Bayes increasingly. One of the ones that I particularly like is Jim Albert's Learn Bayes package. There's a Springer population that goes with it out of the useR series. And the code for these things are available. It's actually it's something I recommend to students when to kind of get them to the place where we're going to actually do real modeling. The R language is also convenient for rapidly prototyping things. So it's not unusual that you might try to implement a new algorithm in R and then find, geez, you know, I just can't wait for this thing to finish. So you might decide that basically to up the ante and code it to something like C or Fortran and then call it from within R. That's not unusual. A lot of the packages do that, particularly the ones that do markup chain Monte Carlo simulation. R has very superior methods for graphics and data visualization, which is now sort of at the heart of ours. It came from S, from Bell Labs. It has packages that, like Lattice, which came out of the Trellis package in S, ggplot2, which is based on Wilkinson's grammar of graphics, and a variety of things that make it easier to actually try to visualize the results you're getting out of models that are kind of very large parameter space models like these. And then, as I kind of mentioned, some of the computation makes more sense to do outside, and R makes it possible to access algorithms or sampling engines for Monte Carlo simulation in other environments. So in particular, the environments include Bayes updating with Gibbs sampler is actually kind of an R public domain version of a platform that was originally developed at Cambridge. Just another Gibbs sampler, Mark Plummer package. Scan, which is from Andy Gelman and his colleagues at Columbia. And then, of course, you can write code in other languages, increasingly even in scripting languages like Python, and I expect to see something in Julius if you call. So if you find you can't get enough velocity out of however it is you coded in R, and you don't have the opportunity to take advantage of parallelization of your code, then in fact, the next strategy is to kind of move to something that's going to execute faster, take advantage of R's ability to manage the data, to publish results, and so on, and to set up a run, submit to an algorithm that's running outside of the R environment that is called, and so on. And finally, R, of course, has nice tools for accessing databases and proprietary data files that come from different systems. Maybe not as much as some other packages, but it's definitely in there. I don't actually use a lot of proprietary data formats, so I'm not really up to speed on kind of what's available. And finally, last but not least, as you know, there's a very, very large and active developer and user global community for R, which is a lot of where kind of the real value and power is coming from in this environment. It's kind of like Linux, right? Or Python. And so that's a real advantage. Chances are that whatever it is you're trying to do, somebody has probably done it. And if you're a believer in not reinventing the wheel like I am, I mean, the first thing I'll do is I actually look for examples online. And it's true with graphics too, right? You know, if you want to figure out how to write the code for graphics, you look for some example somewhere. You look in a library. If you want to know how to do a widget, you look for an example. And so that's what's really very different than not many decades ago. You know, we didn't have the ability to basically search the internet and look for solutions to problems that we thought we'd have to like go to the library and figure out. So anyway, those are a number of reasons why we would do Bayes and R. I mentioned that these methods, when simulation techniques are used, are very computationally intensive, and that's often one of the challenges in R. R is not the quickest tool in the shed, and also it stores results in RAM. So there's certain constraints on how much you can do at any given time. One thing you learn in regard to ladder is save early and often when you're running in sessions, because you know, if you have a power outage or something like that, you haven't saved the content of your session save that image, open quote parent. They're going to be, sorry. But anyway, by and large, despite the kind of constraints, there's been a considerable growth in tools for doing Markov chain Monte Carlo estimation, Bayesian hierarchical-based models in particular, by taking advantage of the ability to call code that's written in some compiled language you call from outside and so on. And that's good because this is basically, these are the techniques we use to estimate the parameters of really interesting and useful models. The class of simulation techniques in general is referred to as Markov chain Monte Carlo simulation, and for obvious reasons. At least it's a name that means something, right? So it's Monte Carlo simulation because we're making some draws from some distributions. It's a Markov process because the draws are conditional on the previous iterations set values that we draw. So it's Markov chain Monte Carlo estimation. The samples that we draw over successive iterations are referred to in the vernacular as chains. So you have, for each parameter, you can have a chain that you generated by successive iterations through the algorithm. And that chain actually, once it's met your requirements for stationarity, if you will, actually allows you to use the data points that are generated after getting rid of those that have been prior to the thing stabilizing to make inferences about the distribution of that parameter. I'm going to give you some examples of this. And there are several different flavors of this kind of sampling algorithm depending on the parameter of interest and some other constraints. All right. Any questions so far? Going too fast? Too slow? Not jokes? Okay. There's more and more Markov chain sampling algorithms all the time. But these are kind of the classic ones. And they're basically distinguished by one important difference. Actually the simplest one, and I'll show you a very, very simple example of how this works in a minute. It's referred to as a Gibbs sampler. For the life of me, I don't know why it's called Gibbs, but somebody knows that. I keep forgetting to look that up. But it was actually described initially in the early 80s. And then it was actually sort of additional interest in it was stimulated by this paper by Galbraith and Smith in 1990. And basically, the idea is basically this, that rather than calculating densities sort of algorithmically or in a closed form solution, what we do is we generate random variables indirectly from these distributions. And then we use that to typify the posteriors of particular parameters of interest. Gibbs works when you can actually sample directly from the conditional posteriors. So you have to be able to make a conditional random draw from the posterior distribution. Not all distributions like that. Gaussians are really nice in that regard because you can do that. It's really easy to sample from a normal distribution. Other distributions like scalable chi-square are not like that. So you have to do something different. So there's a set of related sampling algorithms called Metropolis, named after the guy who authored the paper in 1953 after it's classified. And Metropolis Hastings, which is a paper, a generalization of Metropolis by Hastings in 1970. And this is an algorithm that's used when you can't actually sample randomly directly from the posterior of interest, but you can evaluate if you can actually come up with something that looks like a point from that distribution. So you use kind of a proxy or a surrogate distribution, it's called a proposal or jumping distribution, to make a probabilistic statement that you should from that distribution or keep the one that you got in the previous iteration. And there's actually, this is a pretty well understood algorithm. It's just more computationally complex and it takes a little bit longer to run, but it's fairly commonly used in complex models like hierarchical multinomial logic models. It costs us the complexity and it runs slower. But there's some distributions you just can't continually sample directly. So here's Gibbs sampling in R, okay? So this is the simplest example of how Gibbs sampling works to actually approximate a density. And so what I've got here is this like baby function I wrote in R, right? And I called it binary Gibbs. I should have called it baby Gibbs. But basically what this function does is the following. It actually accepts two input parameters and an R, and it's the number of iterations, of Gibbs sampling iterations I'm going to run. R is basically the correlation, a specific point value of a correlation between two variables, x and y. It defines kind of the shape of the normal distribution of the density. And so the way that algorithm works is, so we know how many iterations we're going to run n. We know what the relationship between x and y is going to be to R. So it starts off with basically setting initial values for x and y. We set up a 0, and then it just basically sets up a way in a matrix to store the successive pairs of values that we're drawing. And then we just do the simple for loop. It starts from the second, because we have the first point, and it goes n, however many n we decide. And basically it says, and this is the gives part. So it says, okay, what's the value of x? X is a random draw from a normal distribution, a single draw, with mean r times y, whatever the value of y is at this point. Whatever the last value of y is that's available. It started at 0, but every time we iterate, we get another y. And so we're assuming, and here's the key insight, we assume we know y. Right? What we did, we sort of had a value from the last iteration. That's all we know about y so far. And the standard deviation is d, which I just basically thrown out there. And then the next step is, oh gee, now, how do we get a new value of y? Well, we pretend we know x, and we do. We just drew a value of x. It was based on the value of y that we just had from the previous iteration, right? And so we keep doing this and doing this, and we get these pairs. So here's what the behavior of the sampler looks like over successive numbers of iterations. So this is 10 iterations. And you can see it starts at 0. The line segments connect the successive points of the algorithm. Right? So there's 10. There's 100. There's 1,000. There's 10,000. And so you start to see sort of a bivariate normal there. What the algorithm is doing is it's kind of exploring the space, or kind of a bidimensional support for this distribution, and it's sampling. And basically it piles up more and more spaces where it's got a higher density. So you might call it a fuzzy bivariate, or a prickly, porcupine bivariate. But anyway, that's how gibbs sampling works. That's all there is to it. Now, if you have a lot more, if you're drawing a lot of parameters, and there's a lot of interdependencies between them, of course the actual algorithm gets more complicated and takes longer to run. If you were to do the same thing for just basically linear regression, it's not that much more complicated, but you have to know what the priors are. So, for example, this is kind of the standard linear in its parameters linear regression model, where y sub I is the dependent variable for case I. We basically would say, well, reasonable prior on the beta's regression coefficients is they're normal. So that's what that is. We have to pick out some prior for sigma squared for the error variance, that, you know, the little epsilon's distributed, we assume it's normal with expected value 0 and sigma squared. It's constant for all epsilon sub I IID, right? And we have to pick out what that is. So it could be inverse gamma, it could be inverse chi-square, it could be uninformative, right? You know, bounded uninformative. We can just say, well, it's flat, we just figure it's between 0 and 1,000 or something like that. That's really uninformative, right? And then basically we have to figure out what the likelihood is. Well, this is the standard normal likelihood. And then actually based on these things, we write the joint posterior, these two parameters, whose posterior densities we want to use for inferencing, beta and sigma squared. What does the gibbs sampler look like for that? Actually, this is the hard part, right? Basically, you start out just like we did before, come up with some initial values, and then what we do is we iteratively go through this process over and over again. We draw values of beta given what we know about the data, and the most recent value is sigma squared. And then we pretend we know what beta is. We draw values of sigma squared given the data, and the most recent value of beta. And we just do this, we just keep piling them up, and we go until we're done. And that's all there is to it. So that's the gibbs sampler. There's some little details. One is this notion of thinning, and that's that for a variety of reasons, not the least of which is that actually this can consume massive amounts of storage, that we don't always keep all the sampled iterations, but we may keep every 5th or every 10th. They will be autocorrelated because they're Markov, right? So everything is drawing conditional on the previous value. So if you did an ACF and looked at it, you know, it'd be huge. But there's certainly to suggest even if we ignore that, we actually get pretty good approximations of posterior density. But that's less of a problem if we're taking every 5th or every 10th. The other reason is, well, of course, if you're running this in R, this stuff's piling up in RAM, right? So, you know, you start to get things that are like, you know, get close to like a gigabyte, and that thing's sitting in memory. And you're going to also analyze that. So there's another reason why you don't necessarily want to keep it all. And of course, there's the other point that I made that, in fact, these things can be arbitrarily precise if we run them long enough. So if we wanted to make this a binary probit model, actually there's a very simple trick, which I won't spend a lot of time on here, but it's something that's worth knowing about. It's actually a way of making inconvenient either ordered or unordered discrete dependent variable models estimable just by using a simple trick that's called data augmentation. So data augmentation is really this idea of adding a latent variable that's a continuous one that doesn't really mean anything, it just simplifies our calculation. And it was the technique was originally described by Tanner and Wong in a Jazz paper in 1987. They have a Springer series book about this. And Jim Albert and Sid Chip in a paper in Jazz in '93. It was particularly about binary and multiple category ordered probing models. And the way it works really is you just introduce this additional variable, and then actually you pretend that variable is continuous. You treat it like the y in that linear regression model, but you actually sample it in a truncated way based on the actual observed value of the dependent variable. So it works for binary dependent variables. My colleagues and I have used it for like ordinal rating scale data, where we're also actually estimating the actual cut points at the same time. Those we actually put non-informative priors on. And it's actually, so you can actually end up using kind of this give sampler idea very easily just with this little caveat of using this data augmentation technique. It's a pretty cool thing. All right. So not surprisingly, with models like this, there's a whole bunch of things you've got to watch out for, and things you do to kind of fully evaluate the model. Here's just some of the high points. One is this idea of this burn-in. You kind of like to make sure that you've got enough iterations and you can throw away enough so that what you've got left actually reasonably convinced are draws from stationary distribution. If a model is not well specified, you've got identification problems. Sometimes it's pretty apparent, sometimes not. And I'll show you an example of when you don't have that in a minute. Base factor is a way of comparing two different models. It's basically just the odds, it's the log odds of the posterior, it's the ratio of the posterior likelihoods, basically what it is. So it's kind of equivalent to kind of like a wall test, but it's a Bayesian test, and it's kind of an index. So there's different rules of thumb that get applied to deciding how big it needs to be before two models are different, how well they describe the data. But that's kind of the common, sort of one of the traditional ways of comparing models. Posterior predictive checks basically are sort of not strictly Bayesian, but what they consist of is basically using your model to generate distributions of the data you've actually observed, to look to see whether in fact those generated values, given the uncertainty in the model parameters actually, whether the actual true values actually sort of sit in this generated distribution. I say it's not strictly Bayesian because in fact you're sort of using data again at that point. But oftentimes you'll see work where you see people who are generating these posterior check distributions, and you'll see a line that's the actual observed y value, and then you'll see a distribution that's generated predicted y. There's some kind of fairly common methods for, at the kind of model aggregate level for estimating model precision, like mean squared error, mean absolute error, deviance information criteria. There's sort of an asymptotic to use for Bayesian models. It's kind of like BIC, like Schwarz's criterion. Various kinds of log likelihood functions, and root likelihood, which is the geometric mean of likelihood. That's a measure that's actually in particular used for certain types of choice models, where the idea is that a model is performing a chance will have a root likelihood is equal to the number of choice alternatives, the average number of choice alternatives. You can actually generate an uncertainty distribution for that because you have the information in the chains. And then there's various tools in R in particular that can be helpful. They all have kind of their little quirks. There's packages like Coda and Bo that actually apply different summary statistics to chains to see if these stabilize. And then also allow you to make chain plots to take a look at those. And then several of the packages have their own methods in them that are more specific to the particular type of Bayesian models that are being applied. Last but not least, this is something I talk about with my students, and that's what I call the sniff test. Look at your summary results and actually see if they kind of make sense. Well, this is subjective anyway, right? So do the results kind of look like what you would expect, or is there something seriously wrong? So something seriously wrong would be like you're estimating demand and it looks like the price coefficient is positive for demand, or chances are there's something wrong there. And you should go back and there's a problem with the data or the model or something. The more complicated the data collections and for the modeling procedures, the more likely it is there's things like that that will be kind of nuanced, and you have to look at them very carefully. But I call that the sniff test. It's definitely it's technical, right? Okay. I don't know, I'm not sure if I mentioned mixing or not. I might be having a deja vu experience here. But one of the things you look at in these chains is actually whether they look like they are sequences of draws from stationary distribution. And what one would do is basically, this is a change of 6,000 after thinning from 30,000 from a hierarchical multinomial logit model, where this is right from the beginning, so we're starting right from initial values, in this case for this regression parameter, this initial value of 0. And what we're looking at is, if we look for here, does it look like pretty much it's just like successive draws from something that's a reasonable symmetric distribution? That's kind of what we expect, especially since the prior we put on this stuff is multivariate normal, right? And we can actually take some of these. We might say this is our burn-in. We still got 1,000 left here, basically to describe a distribution. It's pretty good at here. We can look at that, plot the density of it, and say, does that make sense? This one has got some problems. This is what's called poor mixing. You see this kind of low frequency oscillation in there. It's almost like there's some kind of random walk that's kind of stumbling around. This is the kind of thing you see when maybe there's a parameter identification problem involved, or there's something else going on. But one of the ways that people tend to diagnose how good their models are, even though in principle you may have thousands of these plots you can look at, is this notion of does it basically pass the visual sniff test? Does it look like that? I have a friend at Ohio State who's been doing this stuff for many years. We often talked about this stuff because I've often had to explain to students about, yeah, you make 1,000 graphs and look at because there's no theory that says, even if you look at some of these, there's no theory that any of us knows about that says that everything will converge to stationarity at the same rate, regardless of what the model specification is. So some things could, some things may not. Some submodels may for some respondents, maybe not from others. And so even if you aggregate across all that, you might actually just be masking like parts of the model where you're having some real problems. So my friend at Ohio State's gotten to the point, I guess he just sort of jaded or decided his time is pretty valuable now. He says, well, look, I'm from Ohio, and he said, if I look at it, it looks flat as a cornfield, and I'm happy. And that's his sniff test precision. But this mixing problem actually can be, okay. All right. So I want to spend the next several minutes, I'm going to kind of walk you through an application that's pretty common in applied marketing science. And before I do, what things have I obscured? What have I obfuscated? Notice it's kind of a lot, and there's a lot of detail, and I'm kind of pushing it aside. But
I was just going to ask on the mixing task, if you could, it seems like a frequency domain analysis or something like that. Are there other sort of types of regressions besides just underlying?
yeah, actually I'm not sure. I know that people have applied like spectral frequency analysis to these things. Try to look at basically.
Does that do it? Are there other variations besides?
No, well mostly. I mean, there could be other problems that you don't see that don't have to do with this mixing. But the one thing we do know is that when it looks like that, there's probably an identification problem in the model. Now, the other thing that I didn't mention is kind of good model-like practice. It's not unlike other kind of practices. We should actually start with different initial conditions, initial values. In Bayesian stuff, you should do sensitivity analysis in regard to how you parameterize the priors, the hyperparameters, because you have to describe those, right? You have to say, well, it's a normal distribution with some variance. And all that stuff basically gets combined with the likelihood you get in the posteriors, your results depending on what's happening in likelihood actually pretty sensitive to the priors. There's an adage in kind of the world practice called the data dominates the priors, but only if you have enough data. So if you don't have a lot of data, your priors will be very influential, because it's like an observation that you had prior to collecting data, right? And they get weights when the priors and the likelihoods are combined and you get the posteriors in the sampling. So good practice is just like in other areas, you consider alternative initial conditions to see if it's in the same place. A common example of that is basically running k-means clustering and not starting with different seeds. Where the data, or in a case where you have in maximum likelihood estimation, maybe the likelihood function is relatively flat. So, you might do some steepest descent or still climbing kind of algorithm to get to some maximum likelihood value, but if things are pretty flat, then in fact, you might end up somewhere else if you start with additional, different initial conditions. Or problems with like ridge kinds of problems. So, you don't escape that when this. In some ways, maybe it's worse. And then they're also running parallel chains. It's not unusual for people to run parallel chains for the same parameter if the problem's not too big to allow for doing that. Okay, let's talk about something different here. So some of you probably know something about conjoint measurement in here. And this conjoint measurement is actually a way of decomposing the components that explain people's preferences for alternatives. It does so kind of quantitative way using experimental design procedures. It goes back to work in the early 60s. It was initially published in the mass psych literature by Dr. Lewis and John Tukey, the same John Tukey that you're familiar with. And ever since then it became, well, from that time it started to become popular in areas like in marketing, research, and science for product development. In the early 70s, it was popularized by guys at work named Paul Green and Jerry Wynn, who wrote kind of the breakthrough in terms of public interest with a paper that had HBR, Harvard Business Review. Turned out actually, Paul Green passed away some years ago, but he told me that actually they made up the data for that paper. Because he said that he and Jerry talked about it, they thought it was just a magazine. So what the heck, you know, it was a paper about toothpaste dispensers and how you design them, you know, so that people would most prefer the dispenser. Well, but they actually were legitimate scientists, and Paul and Jerry, who's still around, they contributed very heavily to this area of measurement. But anyway, the idea is basically that you construct a set of stimuli that you're going to show people and they're going to respond to. The stimuli are such that they're based on an experimental plan, so you can estimate the contribution or impact of every different characteristic or attribute of the stimuli on decisions or choices that people make. And it's kind of a repeated measures exercise, and so most of the time. So what that means is actually you get sufficient amount of information for someone who you're asking questions of to estimate individual level parameters for a regression model that predicts functions or preferences. The responses can be varied, so they can be choices, they can be rankings, they can be ratings. So this is a little bit different than, say, the problem that online companies have in modeling for recommendation purposes. Because here what we have is something we're using experimental procedures to get good, fairly independent estimates of the different components that are driving people's choices and preferences. And also, one of the main advantages of this kind of technique is you can actually test out ideas for things that people have never seen before. Now, there's some problems, and of course, making the task manageable and doable for them and having them understand what it is you're talking about. So there have been kind of extensions of this technique to do things, for example, like to estimate the demand for General Motors EV London car, which actually the demand estimates were pretty good. It failed for other reasons. It seemed to be kind of political economic. But those exercises were called information acceleration, and they had embedded in these kinds of choice tests. But they put people in what in those days was sort of this very rich multimedia environment to get them better understand what the world might be like, or an electric car might be something worth considering, gas $10 a gallon. So anyway, these are most commonly, this technique or class of techniques is most commonly used in quantitative marketing science and it's a research method. Okay. So, what would you use it for? Well, you might use it for designing anything. You might use it to understand the preferences for people applying to biostatistics graduate programs. For example, how important are things like cost of living? How important are the reputation of the faculty and so on? Assuming that you can kind of quantify those in reasonably objective ways, you can construct a task. What do the stimuli look like? Well, here's an example from a study where I kind of disguised it a little bit to protect the guilty, but this is from a study from a few years ago. Where somebody in the Bay Area who had a recent liquidity event in a high-tech startup had decided that they were going to go into the custom yurt business. And you probably know what a yurt is, but it's a circular dwelling that was basically traditionally from places like China and Mongolia. They have a lot of advantages. So Kurt, changed his name, decided to collect data from people he thought would be in the target market for these custom yurts, right? Other wealthy Bay Area young people, right? And he wanted to figure out, like, if you could design a single yurt, which one would be most preferred by people in his target market. So you have to have a sample that you can generalize from. And you construct a task as part of the survey. And the task presents a series of questions like this. This is called a choice set. And this has basically 3 different yurts described by these characteristics. They're called attributes in the vernacular, but they're basically experimental factors. And the factors have conditions, and conditions are called levels. And so this yurt number 1 does have a solar-powered fan. It has 2 doors. It has 2 windows. It has just their standard fabric, however Kurt defined that at the time. And it has 30 feet in diameter. And the price per square foot installed is $50 per square foot, not including the property. He actually called it his products. This is true. Kurt's outstanding yurts because he thought they'd be outstanding and beautiful places. But His name started with C, but it was true. Anyway, and so the other thing is different that sometimes you don't find in some. So you use the experimental design to specify these combinations, and you show these a series of these things to people, and they give you their choices in each one. Something you don't always see is actually I wouldn't buy any of these things option in here. Economists call this the outside good, but it's just a way of kind of getting a better sense of what the demand might be. Because alternatively, you could just say which one do you like best, and you understand the distribution of preferences, but it doesn't tell you as much about whether someone would be likely to pony up for any of those things. So anyway, that's what the task looks like. And underlying that, the modeling of these things, most of it draws from work that's been done in what's called random utility theory. And random utility theory is mostly a reflection of work done by Dan McCadden, who won the Nobel Prize in Economics for it. But basically the idea is that actually underlying these choices, there's a latent variable, a continuous variable that we call utility. It's kind of like a value construct, but it's sort of economic. And it has two parts. It has a deterministic part, and it has a stochastic part. And basically, the stochastic part is kind of nice because just like an error term in any other kind of predictive model, it allows us to be wrong some of the time. And basically what we have here is just, it looks like a regression model, right? It'll actually be a discrete, limited dependent variable regression model in most applications, where the x's, the design matrix, describe the particular values on those factors or attributes. And the betas are actually the regression coefficients, sometimes referred to as utils or utilities or part worse. The jargon's a little bit confusing, but they're regression coefficients when you estimate the models. So these models are actually called random utility models or RUMs, and when we talk about them, when someone's doing that work, we say, he's in the RUM again. But in fact, that's what we refer to those models in. And they may or not actually, we don't believe this is what happens when people do this. And we know people are Bayesians, and we don't believe either linear models, we suspect. But these are models, and they don't need to be correct, they just need to be good enough, right? Or better than other models. And so as I mentioned, Dan got the Nobel Prize. It actually turned out that we were doing some background work for a paper related to this that we did a couple of years ago. We found some related work in 1957 by Atchison and colleagues that looked very similar. The only difference was McFadden basically gave these little epsilons an extreme value distribution. These guys, Atchison, said that they were normal, so it was a probit model. And so our takeaway from that actually that to win the Nobel, you can't be normal. And so, sorry, it was a dead joke. But anyway, they're underlying these choices in the models. There's sort of this theory that comes from economics. So it's the kind of model that we tend to pick. So oftentimes my colleagues and I, for research purposes, tend to use more multivariate, multi-category probits. But multinomial logits are actually often used a lot because they have certain computational advantages. And the models look like this. So there's a multinomial likelihood. It's the standard multinomial likelihood. It has a Dirichlet distribution prior, right? Then we have these underlying things, or these latent variables, those are called utilities, and they're a function of the deterministic part and the little epsilons. We put a distribution on the beta sub i's. Now the sub i's, the betas, these beta vectors are actually specific to individual respondents. So if we, as you'll see in a minute when I show you some data, some results, we had 360 people do this particular task of data I'm going to show you it came from. Each of those 360 people has their own beta vector in this model. That's both, we just basically say we give it a prior multivariate normal with mean beta, expected value, and a covariance matrix V sub beta. Standard prior on that kind of covariance matrix is inverted Wishart, and filled with the hyperparameters for that to get it to be the right shape. Now the other thing that's kind of interesting about these kind of models is parameters have parameters. We can add an additional layers that explain things like the betas. So we can actually make the betas dependent variables in another layer of regression coefficients in these models, right? So parameters have parameters. And so we can, for example, say, well, look, the beta sub i's are a function of these things that we know about people, maybe their prior brand ownership or demographics. So these variables here, these z's, become regressors for the beta sub i's. And we have to do the usual thing. We put priors on those things and we give them multivariate normal distributions and so on. Now we could put a mixture distribution on them and say, well, we think actually the sample we've got is from two different populations of people who have different distributions of the regression coefficients are part of what's, we could do that. Here, this is just basically a linear regression model, but it's an additional layer. We'll call that an additional layer. So those z's, those are covariates of the regression coefficients, right? The beta. And the psi's are regression coefficients from regressing the betas on the z's. Okay. So when we do these things in R, there's a bunch of things that are already in there that you can use. There's a package written by a colleague of mine, Peter Rossi, called Bayesian. I'm going to show you some results from one of his algorithms in a minute. Choice modeler is a little bit more recent. It actually calls the same routines that Peter's routine calls. Then you can actually, without much difficulty, right, in the specific package language of these different packages you can call, do the same kind of estimation. One of the things that's different, for example, in the bugs language is a declarative language. It's not a procedural language. So you write things as if they are loops, but it doesn't actually execute the loops. It just knows that that's what the embedded nature of the different parameters are in the distribution. RStan uses different samplers. It uses the Hamiltonian. It used to be the hybrid Markov chain, kind of gets you the same place. It also has nuts in there. I don't know if you've noticed that. The no U-turn sampler that they call it. They actually all have their own idiosyncrasies. So sometimes when you're doing these models for real, you might use really different simulators to see what you get. And JAGS is another Gibbs sampler. So those things, along with all the other tools that I mentioned previously, give you a pretty substantial arsenal for doing these things. You just need to have time. Okay. Finally, so we're getting down to the bottom of the hour. I'll just spend a few minutes kind of giving you a flavor of a particular application using these techniques to model the structure of preferences. So these are data from a study that's slightly disguised, a few years old, that had to do with the design of tablets like iPads. And it was for a company that was in the business of consumer electronics, didn't have this kind of product in the market. And they wanted to understand what the important determinants of preferences were for tablets of certain configurations. So they did, in their case, fortunately did reasonably good previous research that involved a lot of qualitative work and secondary research looking at the market, talking to people in groups and visiting people as they use their tablets, and tried to sort out the various characteristics they thought were the key determinants of what people would prefer when they were thinking about buying a tablet. And so what all that resulted in was a choice design that had 36 choice sets with 3 alternatives each. If you think back to that thing about the yours that had 3 choice sets, there were like 36 of these that described tablets in these characteristics. The attributes were how much RAM did they have. There were 3 levels. There was 8, 16, and 32. Screen size 7-inch, 5-inch, 7-inch, and this sort of mini tablet, right? 5-inch, 7-inch, and 10 inches. Processor speed, I can't remember what they were, but there were 3 levels. Maybe 1.62 and 2.5 or something like that, gigahertz. 3 levels of price, $199, $299, $399, and 4 brand names, which I'm not going to mention. And so this design was constructed actually using an algorithmic procedure. So it was a reasonably good compromise between the precision of the estimates and not having too long a task. It also allowed it to estimate coefficients for certain interaction components. And in particular, they were interested in brand by a price component interaction because their theory was, or what they were guessing, is that price sensitivity would vary by brand. And that's often the case, one would think. And it might be related to other things. So there was additional data that was collected. This was done online and an online survey. And so that's what the data were like. So these results, actually, they were analyzed in a bunch of different ways. I actually have some students doing this right now, this way. One way that the data have been analyzed, and the way they're doing it, is to use this particular procedure out of Peter's Bayesian package called PAL, easy to say, all higher MNLDP from this package. And what this is a hierarchical multi-nominal logit model with a drill-shaped process prior on the multivariate distribution of the data. And that's purely a pragmatic variation on this. And the reason is that what many have observed over time is multi-nominal logit models with multivariate normal distributions on regression coefficients tend to have tails that are really thin. So the drill-shaped process prior is actually a way of basically saying, well, we actually might have a mixture of people with tails of different things in your distribution. And we can actually estimate dynamically through the iterations how many of those components there might be. And in fact, that's how you go about doing non-parametric mixture models using Bayesian techniques. And it's just sort of in there. Sometimes you can see the difference in sometimes you don't. But in this particular example, that's kind of the technique. What's smart about it, actually, if it doesn't need to add components, it doesn't do it over iteration. But you can see the progress as you go through the chains, because for every iteration of the algorithm, you can see the components that are being added or not added. It's kind of a nice thing. 30,000 simulation runs, thinned every fifth. These kinds of models, typically these multinomial logic models, you need a lot of iterations compared to something simple like a Gibbs with just mostly normal distributions. We've thinned throughout the first 5,000. That left us 1,000, which really corresponded to 5,000 iterations out of 30. And of interest in particular for marketing purposes would be things that have to do with the distributions of the betas and the deltas, and I'll tell you what those are in a minute. So the deltas are in the beta covariance. Remember that model I showed you that there's the size that actually related to beta sub i's to the z's. That should have been size there. I messed up my slide. And so here's kind of a very small piece of what the results look like. And then I'll point out a few things that actually will illustrate the kind of inference that we would do and how you use these results at the end. So up the top, basically, is kind of how it is that this particular procedure is called an R. And it's basically an R, every result is basically an object. You have to assign it to something, otherwise you're just going to fill your console screen and you won't have anything left. Everything in R is an object, right, pretty much. And basically, it's the arguments that it's calling here, these are required. Data 2 is actually a list of data lists. So it's a data structure in R that's organized by respondent and by their choice responses in the design matrix. And this MC thing actually here is another list that just specifies how many iterations we're doing and we do things like that. So you run this actually on a laptop, you know, like a modest one, well, maybe one of our Macro Pros. And it might be a 20-minute run to do this. And it's actually running in an optimizer in C, but there's a lot going on here, right? So my advice to students is, you know, if that's what you're doing, go get a beverage of your choice, because and save it for sure. When it's done, save it. And so what this returns is what a lot of the routines in R returns. It returns a list, a list of data objects of results. And in there are things like, these are the beta draws are actually a three-dimensional array that's basically, it's 360 by 14, there's 14 regression beta coefficients in this model, by 6,000 when it comes back. Remember, we're going to throw out the first 5, right? And delta draw is actually that, it's the delta I mentioned before that should have been on the side. But those are the draws, the chains for the coefficients from regressing the beta sub i's on a couple of different covariants that actually in this case happen to be previous ownership experience indicator and indicator for whether the respondent is seeing it or not. And then a variety of others, chain for the model log likelihood. Right. So all of this is coming back, they're all chains of various kinds, and they describe things like the Dirlichet process mixture and so on. So all this is actually, this is kind of what I said, results overload. You really got to know what's important here, otherwise you're going to spend a lot of time looking at all sorts of things that are interesting that are not going to help you answer some kind of decision. But anyway, here's the chain for the log likelihood, right? And you can see basically it starts from some very negative value, and it goes up, and it's pretty flat. This is the chain for the third regression coefficient for the tensor respondent. And here again, this looks like, it looks pretty good. Lots of dots. So 6,000 samples. That's thin from 30,000. And we're going to use, in a minute, I'm going to show you kind of some summaries of this for inference purposes there in the last section. So I mentioned earlier the kind of the sniff test, right? And one thing we like to look at initially is that, you know, at some aggregate level, does everything looks like it makes sense, you know, or things look backwards. What do we know about this? Well, I've labeled, these are the means over respondents in the last couple of thousand draws. So we're taking the means for each regression coefficient for the last 1,000 draws across all 360 respondents. Now, these respondents are all probably from the same universe. So there should be some similarity between them in terms of what the regression coefficients are. We should sort of see some overall patterns that make sense. And one is that we know that this is the effects coded value for whatever the middle level of RAM was. And this middle, and that's highest. And so it's always a emitted level because we've effects coded here, but we can figure that out by derivation. We know that it has to be negative for the sum of these two. So we can actually get that out as a full part word. Well, what makes sense here is this. Look, actually that the largest regression coefficient, it has the largest value. We'd expect that the larger the amount of RAM, the more positively it should affect overall preferences. So that kind of makes sense. Screen size, same thing here. Remember, there's a missing one here. This one will be negative because these are all effects coded, so they're kind of ifs-and-buts. Midpoint largest. CPU speed, low, medium, and high. Price, actually. Now, price should be just the opposite, right? Remember, there's a lowest price level that was the reference level. Here's the mid-price level. This would be what did I say it was? $299, $399. So you can see that, generally speaking, these kind of things make sense. Now, these are kind of so aggregate, we would never use these unless we were forced to support decision making. But now we can actually do the same thing and look at selected percentiles that describe the densities for individual respondents now. So here's respondent 4. And we're looking at the 50th, and 95th percentile of responding 4's 14 regression coefficient. This respondent 4's beta sub i's. And these are, we could actually make the graphs, the density if we wanted to, but we can look at these as a summary and basically say, well, do any of these look like they're different from 0? And let's see, well, if we look through here, wow, that one doesn't. This one looks like that density is below 0. Look, the 95th percentile is negative, right? So if we were to look at that picture, we would say, yeah, well, that one's different from 0, most likely. Right? Remember, these are random variables, so there's no true unique value in the population. They have uncertainty around them, and this describes their uncertainty.
So it's a way to interpret that from the data that's up there, that the CPU speed, I guess it's speed, is the most important element that people are looking at, followed by, I guess, maybe price, or maybe, let's see, maybe it's the amount of RAM.
Yeah,
Would that be an appropriate method of thinking about those results?
Yeah, with a caveat. In fact, a traditional method, it's kind of a legacy method for this thing. There's actually a specific quantitative metric called attribute importance. And an attribute importance is the percentage of the overall range and all of the attribute levels hard worse. So it's like a percentage out of 1,000. Why it has to be considered with a grain of salt is it depends on the attribute levels you're using. So if we had a different level of RAM, because right now we're not seeing the specific,
Right.
that would change. It could change. But
Yeah,
generally speaking,
but given the data, that would be the...
that's right.
Yeah.
Given these specific values, the specific experimental conditions that we use. Yeah, that's right. And here all we're doing is saying, these are just means, but now for this particular respondent, we can describe and summarize the densities, the distributions, the posterior distribution of every one of those regression coefficients. So now what we have, getting back to this sort of results overload, actually what we have is this represents kind of the interesting problem in post-processing data analysis. And it's really, what's happened, the way I think about it is, we've run these algorithms, the model looks like it's performing adequately, now we've got this whole new complex data set to look at. And now we can start describing it in different ways and using it for making inferences. So I'm running over, I'm going to finish in a second. All right. So we can ask questions like, for that respondents, is there likely to be a difference between the price level data, regression coefficient? That's actually pretty easy to do because we just difference those chains and look at the distribution and describe it. And then the question would be, well, how different is it from 0? It doesn't look too different from that. So I wouldn't say, it's not really that likely. Using this kind of analysis of the posteriors. No t-tests, no asymptotics, no p-values. Just look at that. In fact, here what I've done is I've used this as a function, built-in function called empirical CDF. And I've actually said, define the function and then tell me what the percentile is of 0 in that distribution, the difference distribution. About 18%. So 18% of that, of the density is below 0. And I'm saying, yeah, I don't think it's really that likely. There's something there, but you don't kind of get around that problem of figuring out like how big is big, but you actually get a much richer picture. Okay. And finally, I mentioned that there are these beta covariates that I've given different names to at different times. And so basically what we have here is, here's the summary of those what I call them, they're the delta coefficients or the size. These are the regression coefficients for regressing the beta sub i's on the indicators for prior ownership and for female. And you can look at these things in the same way. I could make graphs here, but it's actually kind of a nice way to start just looking at the percentiles. I know what the median is. I know the 5% part, what the location is of the 5th percentile and 95th. And I can go through and do the same analysis.
This may be kind of pedestrian. One of the things that would be very helpful is if you just replace the 3-digit precision numbers with colors.
Absolutely.
Then you can just glance at it.
Yeah. And
rather than having to like scan it.
given the amount of results, actually this really lends itself to data visualization. And then the question is, how do you describe these things? But that's exactly right. So.
Sorry, it's off topic.
No. No, I mean, it speaks to this point of this, you have a lot of results, and then figure, these are the kind of results that, we might look at when we get the initial results we're running, we think are satisfactory, and we're looking at things we might want to represent in other ways. So we present them differently to like management decision-making audience. In fact, there's a lot of this uncertainty we probably wouldn't represent, but that would tell us about what it is we're likely to claim is important to look at. But my point here is just simply to say that every single one of these now has a posterior density that we can describe, and we can use that for making.
Just don't think too much about how color relates to cumulative density function.
I don't know, but I think we need a widget for this. Okay? So anyway, in a nutshell, what this stuff is used for is for product design decisions. Sometimes it's used for things like trying to figure out what messaging should be going in ads. These results will actually oftentimes be put into some kind of simulator that decision makers use for doing what-if analysis and occasionally for optimization. Those are really hard problems, especially since you need to take into account all the differences. To do it properly, you have to do what's called full enumeration. So you have to use all the information from all the respondents and figure out kind of what would be the single best configuration given all of their individual differences and preferences. So anyway, so that's actually kind of an application of this sort of modeling procedure done in R, using techniques that are already in there, and what it is that's used. So, and that's my story, and I'm sticking to it.
You referred to John Cushing. I happened to pick up his most recent book, which is all R-based.
Oh yeah. Nice cover.
Oh.
Lightweight.
And so I'm happy to stick around, and I know it's Friday, but do you have questions? Or?
So in the successive layers of these hyperparameters and so forth, I'm trying to understand when you're doing these sort of synthetic sampling, and I guess I've been confused recently by looking at neural networks and deep learning.
They're all sorts
I'm
of
confused by that.
to some degree.
Where those things basically that different layers recognize they're not dependent on one another in a sense. But if you've got samples and then you're looking at hyperparameters or some sort of characterization of the stage before, and each stage is subsequent. I mean, it's hard to imagine that there is still dimensionality that persists through those depths.
Yeah, that's a good point. And actually, I can kind of give you an
It's not
anecdote.
just reducing to like some single parameter somehow after multiple stages.
Yeah. The trick behind all this is that estimates become conditionally independent of other things, depending on how you draw the model. There's graphical representation of these things in directed acyclic graphs, where it's plates that are actually used to describe the relationship, describe the interdependency of things. And so, not all parameters are independent of everything else. They're conditionally independent of some things, depending on the nature of the dependence relationship in that kind of graph. But you can't, there are, we don't know of any theory, a lot of smarter people than I am that I've talked to about this don't know of any theory that tells us at some point what constitutes over-parameterization, right? Because if you first look at this, you say, well, yeah, sample of 360, you're getting thousands and thousands of parameters. But there are cases where we found that like more complicated models that should make sense that allow for more heterogeneity don't do any better than models that don't. And one sort of pseudo theory that we've got is actually there's just no more information left in the data. You know, it's just not there anymore, to your point. And, you know, that can sort of happen. It's like we've exhausted it all
Yep.
in this parameterization.
That's exact, I mean, you know, I came out of, and I know he's interested in the stock market model in there, that's film in the back, but part of the problem is that so much of the stock market modeling is trying to torture a very small set of numbers that is in fact being influenced by completely outside factors. So no matter how precise you can get the modeling of the time series, it's useless because you're being impacted by outside
Sure. So you have
factors. And so
variables.
you've got a fundamental problem of your model construction to begin with.
Yeah, that's a misspecification.
Yeah.
problem, yeah. We also see that in areas like marketing mix modeling, right?
But at least
There's always something outside, and the best you can hope for is it's more
Not
common.
looking
Because
for
otherwise,
perfect
you
model
know,
for your
you have great difficulty in marketing mix modeling and things like causal inference, because you can see relationships, but you can't satisfy the requirements for valid causal inference, and you may well be seeing things that result from limited variables or other problems, or causing things to be endogenous,
Yeah.
you know?
And to, back to the market example, which we've talked about, is you can analyze the historical market all you want. That doesn't tell you anything because the world within it, which it exists, is not the same world. You know?
People also don't know what they really want.
Well,
This
this
is
that
true.
too.
Sure, well, that's one argument that's made for these techniques, is you know, I ask them, you just make them choose between things. And so, it's not infallible, because what happens with these techniques, there's a whole lot that happens between when you do these measures and when something gets into the market. And, you know, one thing that's actually generally referred to is from an industry perspective, post-lunch new product success hasn't changed for decades. It's between 1 out of 5 and 1 out of 10. So despite all our fancy stuff, like a friend of mine in Maryland says, you know, every time they get papers they review in journals like marketing science or quantitative marketing economics, everyone basically says this is so much better than all previous models. He says, by now we should understand everything. Consumers, we don't do any better. You know? So because things change. Right?
Another very interesting component of that is are you familiar with Nicholas Tille's book and works? I mean, you know, his whole theory about the black swans and the fatted, for so many of what we're trying to model is there's unknown fatter tails that are not taken into account. And that, of course, causes big eruptions in markets.
Sure. Yeah, well, you know, in the area of complexity science, they deal with different sorts of distributions. We deal with kind of sort of symmetric things. They deal with things like power loss, right, and things that exist at infinite scales. And like in the black swan case, it's something that's this really, really rare, really big event.
Yes.
But actually, maybe we've never observed one. It's kind of a black swan event,
Right.
because nobody went to Australia to see them, right? Or they're so rare, like the big one that hit California, right? So their guesses are really bad at best with these things. Because we don't have a lot of evidence, but they kind of exist on. They're kind of scale-free thing. Yeah. Anyway, all right. Well, thank you very much. I appreciate it.
Thank you.
I was going to ask whether we want to do, last time we were talking about an interesting project. I got 2 candidates. Do you guys want to hear it?
Yes.
One is matching medical records, and another one is analyzing Twitter data.
What is it?
Yeah.
I'm more interested in medical data.
Oh, medical data?